So, now we're going to get to the last section. So what was the point of being able to work out oxidation numbers and track what's been oxidized and what's reduced? It's what we use it for. And that's electrochemical cells. Now this is grade 12 work which we're going to examine this year. So it's important that you get this. Okay? So first of all, we need to look at direct electron exchange. Now if you'd watched the animation earlier in the first section, then you'll see when they put the lead zinc into a lead sulfate or lead nitrate solution. I can't remember. The lead and the zinc change places. That was an ion exchange, a displacement reaction, and the lead and the iron were in contact with each other. So we're going to look at that in the same context. Okay, so what we have here is this. So we have a zinc metal plate, okay, that's put into a copper sulfate solution. They are in direct contact with each other. The copper sulfate solution is made up of Cu2 plus ions and SO4 2 minus ions. The zinc metal desperately wants to get rid of its electrons. The copper desperately wants those electrons. So what's going to happen is this. The electrons from the zinc are going to go to the copper. Now pretend each little E is 2 E's, okay? And as a result, we create zinc 2 plus ions and we create copper metal. Now they can't stay like that. The zinc 2 plus ions can't stay on the zinc because it is just not possible. Okay? Now, that means the zinc 2 plus ions are going to come out of the solution, okay, and the copper is going to drop down to the bottom. Okay, so watch again. Zinc 2 plus goes into the solution, the copper comes out. That now changes. My solution was copper sulfate. Now it's zinc sulfate, okay, and it's colorless. The zinc metal is disappearing, and we get we'll get a fine powder at the bottom, which is the copper. There has been a transfer of electrons, and it's been a direct transfer. So the zinc has given away its electrons, and it's given them to the copper, okay. So the electrons were transferred from the zinc to the copper. So the zinc goes to zinc 2 plus 2 electrons. The copper 2 plus takes those 2 electrons to become copper. If I look at this from a net ionic point of view, what we need to remember here is that those electrons disappear when I put them all together. Because what's happened is, even though the zinc gave away its electrons, those electrons are going directly to the copper and going, okay, I'll get used up. So they don't end up in the equation, and they must balance out. Okay? Very, very, very important. So you got Cu2 plus zinc becomes Cu plus zinc 2 plus. Okay? The spectator here is the sulfate, the SO4 2 minus. It doesn't take part in the reaction, but we need it because we can't have ions just running around. You can't have a positive charge just in a solution. It's not viable. It won't happen. It makes it very unstable. So the zinc 2 plus, the SO4 2 minus, is there to neutralize everything. So if I put the SO4 2 minus into the reaction to get my net reaction, I get copper sulfate plus zinc becomes copper plus zinc sulfate. Okay? Now, this is okay. This is great. It's a displacement reaction. We're all happy. It is what it is. It moves on. But it's not overly useful in general situations. So what scientists then did is they went, okay, if we have this direct transfer, is there a way for us to make it so that the electrons get transferred outside of the chemical reaction? So they said to themselves, can I separate the oxidation reaction and the reduction reaction, and therefore make the electrons travel through an electric circuit? And that's exactly what they did. This is how we create batteries. So if we use, and we're going to use a zinc copper cell as our basic cell, and every other cell, which is known as a galvanic cell, is based on the same theory, but obviously with different elements and different atoms. So we're going to teach you how to identify what's what in this. Okay, so what happens is this. The zinc and the copper, we separate them and we force the electrons to move through a circuit. That creates an electric current. By doing this, we make a battery, okay, that you buy in the shops. What's happening is chemical energy is being converted to electrical energy. This transfer of electrons is because there's chemical potential. When the reduction happens, that's chemical energy. When oxidation happens, that's chemical energy. We're forcing that chemical energy to make the electrons move through a circuit. If the electrons move through a circuit, it is electrical energy. So that means I'm going to separate the oxidation and reduction into what we call half cells. And we're going to get indirect electron exchange. So let's look at each half cell separately. So what we have here is we have the zinc half cell, the zinc part of the reaction. In that half cell, you have a zinc electrode and you have a zinc electrolyte. Now, this electrolyte, remember, an electrolyte is simply a solution which is able to conduct an electric current. But what's very important here is that this electrolyte must have zinc 2 plus ions in it. Okay? Must have the same ion as whatever the electrode's made out of. Because if it doesn't, then the reaction's not going to happen the way we want it to. Now, the zinc is attached to another half reaction, and the zinc and the electrons can see what's on the other side. These electrons go, I don't want the zinc, I don't like you anymore, I'm going to go to the other side. Okay? So the electrons are going to leave. Okay, so they're going to go out of the solution so that zinc 2 plus ions get created. So what's happening is this. The zinc is being oxidized. Okay? Oxidation is happening. This makes it the anode. Oxidation always happens at the anode. Those always go together. And because this is the anode from which the electrons leave from, it's the negative electrode. Okay, so the anode is negative. It's the negative terminal of the cell. At the same time, the mass will decrease because zinc atoms are becoming zinc 2 plus ions and they go into the solution. So we're losing zinc atoms. So this anode will get smaller, and it always gets smaller. All right, so on the other side, so where do the electrons go? Well, the electrons then go to the copper half cell. Okay, so the copper half. So the electrons go along, so we have copper 2 plus ions, plus the 2 electrons, they will become copper atoms. This is where reduction happens, and this is now the cathode. So watch. Okay, watch again. The electrons go in, bond to the copper, we get copper atoms, and they go onto the copper electrode. Again, the electrolyte needs to have copper 2 plus ions in it, okay, so they can go into the anode, onto the electrode. This is the cathode. Reduction always happens at the cathode. So oxidation, anode is oxidation, and we have a red cat. Reduction is at the cathode, okay? This is positively charged. It's the positive electrode because we want to attract the electrons to it. Therefore, the mass increases at the cathode because we're making the Cu ion atoms. Okay? So we're all happy with this. But we're not quite putting it all together yet. So we've got zinc happens, copper happens, we're forcing the electrons to move across. But if we just put the two together, actually nothing's going to happen. We need something called a salt bridge. Okay? In the salt bridge, it's made out of a U-tube. It's just a glass tube. We have glass wool. It's also sometimes described as we can use cotton wool. Cotton wool's not great. Glass wool is like cotton wool. It's like a fiberglass, and it doesn't go all smushy and mushy when it gets wet. Okay? Basically, it keeps the solution in so that when we turn it upside down, we don't have all of it running around. Now, the salt bridge needs to be made of a salt solution, something like potassium chloride, maybe sodium chloride. It can be any salt. Okay, so the salt is so it's any salt basically, and the salt bridge has to be made up of ions. Now, it has two functions which we're going to explain in a second. Number one, it completes my circuit. Okay, so it gives a path for the ions to move, and it keeps the electrolytes neutral. This is very, very important. If the electrolytes get a charge, nothing's going to happen. Okay, so this is what happens. The electrons go from the anode to the cathode, and then we get a movement of charges. Okay, so this is the anode. This is the cathode. Alright, and if you watch again, so we're going to go watch again the electrons. Okay, so the electrons, you're going to watch them. They're going to come up here. They're going to go across here. Then they're going to go here. When these electrons disappear, this solution starts to become positive because we keep adding zinc 2+ ions in here. So this becomes a positive solution. Here, we're taking the zinc copper 2+ out. So this becomes a negative solution. That's a problem. Because if this solution becomes negative, the electrons aren't actually going to want to go there. So why? Okay, so what happens is this. The anions, the negative ions, can see this positive solution. So the negative ions go through the salt bridge to the anode. So the anions go to the anode. That's why it's called the anode. The positive ions, which are the cations, go to the cathode. Okay, and these ions also migrate. So these chlorine ions will go here, those potassium ions will go there, and eventually it becomes quite a mishmash of all sorts of things. Why? To keep those electrolytes neutral. So watch again. So everything happens at once. Okay, it doesn't happen in all these parts. Alright, then we create the copper, the zinc goes in, and the electrolytes all move all over the place. Okay? I know that's a little confusing. There are videos on Teams called the Galvanic Cell Part 1 and Galvanic Cell Part 2. Please go and watch them. It's a very nice animation which shows everything really, really well. Everything happens at once, and it's a great explanation. Okay, so that gives us a cell. So what happens in a cell? Well, the zinc goes to zinc 2+ plus 2 electrons. The copper 2+ plus 2 electrons goes to copper. Same as when there was indirect. Really, I don't care about the spectators. There are far too many to put in here. This is the important thing. That the copper 2+ becomes copper and the zinc becomes zinc 2+. Now what's important, what you need to know about one of these reactions. Number one, they have to be spontaneous. They have to be. Okay, they must happen all by themselves. Number two, they are exothermic. That's why your battery gets hot in your cell phone or whatever. They have to be self-sustaining. So it isn't something that we have to keep helping it with. If we have to keep helping it, then what's the point? The point is to create an electric current, so they must be able to work on their own. Chemical energy is converted to electrical. So it's chemical to electrical. Current will always go from the anode to the cathode, then through the salt bridge. And in the salt bridge, it's positive and negative ions that are moving. There is now a potential difference between the anode and the cathode. That creates our EMF. And we're actually going to talk about how to calculate the EMF. But that's for the next one. So, basic setup of a cell. Okay, the zinc copper cell. We have a salt bridge in the middle. The direction of electrons will always go from the anode to the cathode. The anode is negative. The anode is where oxidation takes place, and in this case it's with the zinc. The cathode is positive, and it's where reduction takes place. Okay? Very important. We have electrolytes. Now we can ask you to draw a basic cell. We can ask you to identify a cell. This salt could have been zinc sulfate maybe, and copper sulfate. Okay, this could have been, say, maybe potassium nitrate, maybe even sodium chloride. There are lots of options. Okay, but what you have to know is that the electrons go from the anode to the cathode, and inside the salt bridge, alright, the anions go to the anode, and the cations go to the cathode. Okay, so go watch those videos that are on Teams, and in the next video I'm going to show you how we work out what's been oxidized and reduced if it's something we've never seen before, and I'm going to show you how to work out the potential of a cell.